In this lecture session, I am going to present the topic on single-phase dual converter. In my previous lecture session, we have found that single-phase full converter with inductive load allow a two-quadrant operation. That means quadrant 1 and quadrant 4. When the inductor starts storing energy inside it, then it can provide the first quadrant operation in which the voltage and current both are in positive direction. In case of 4-quadrant operation, when the inductor starts discharging, then it will cover the 4th quadrant operation in which the current is still in positive direction but the voltage appeared across the load, that is in reverse direction. That is why in the first quadrant operation the power is transmitted from supply to load, and in case of the 4th quadrant operation then the power is delivered from load to supply. Okay. So, if two of those type of the full converter that can be connected back to back as shown in the figure next, both of output voltage and the load current flow can be reversed. This system provides a 4th quadrant operation and is called dual converter. Dual converter normally used in high power variable speed drive. If alpha 1 and alpha 2 considered as the delay angle of the both converters, converter 1 and converter 2 respectively, the corresponding average output voltage are VDC1 and VDC2. Suppose the delay angle are controlled such that one converter operates as a rectifier and the different one works as a inverter operation. That is why by both converter which can produce the same average output voltage to the load. This can be further explained by a proper circuit diagram which is given in the next slide. So, this is a circuit diagram for the single phase dual converter in which this part is suppose converter 1 in where we are using the 4 thyristor to form the bridge, that is T1, T2, T3 and T4, and this is suppose converter 2 which is actually connected back to back. That is why the direction of the thyristor are in opposite direction. That is why here that is T1, that is T2 dash, that is T3 dash and that is T4 dash. That means two converters means converter 1 and converter 2 both are connected back to back. And across the both converter we have connected, this is the load. Fine. As well as there is a inductor or reactor we have used to limit some amount of circulating current that will be discussed later. Actually it cover 3 mode of operation, that is for rectification operation, number 2 that is inversion operation, and number 3 that is circulating mode of operation. All operations can be demonstrated by the proper VI plane. That is suppose I0, this is V0. And the load is for application purpose, assume this is a DC motor or DC drive. Okay. Now, in case of first operation, when the dual converter is working as a normal rectification operation, so in which we assume the converter first starts working, that is why then the current starts flowing from the first converter to the load, okay, in this direction. So it will be, the current can be flow, the current is flowing to the load from first converter to this one. Then the supply voltage is positive across the load, that is the voltage is positive, and current is flowing across the load, that is I0 is positive. That will cover the first quadrant operation. Voltage and current both are positive. Okay. And due to presence of inductive load, it will cover the both quadrant, that is first quadrant and second quadrant, right? So we can assume if the load is actually nothing but a kind of DC motor, that means when the first quadrant operation can be covered by using the proper firing angle alpha at the converter circuit 1, then the motor is suppose moving in the forward direction, in this direction. Then it is working as a motoring action. Okay. In case of the fourth quadrant operation, that means when the power is delivered from load to supply, that means this is the concept of back EMF. That means we can say this is the condition for the braking phenomena, and during braking the motor EMF, motor induced EMF, that is called actually back EMF, that should be greater than with respect to the supply voltage. That is why in case of the fourth quadrant operation, then the power is delivered from load to supply. Okay, and this is defined by this region. So we can say in the first mode operation or the first quadrant operation, the motor is working as a motor and its motoring action has been done. In case of the fourth quadrant operation, then the braking phenomena can occur. And in case of the braking, as the energy is feedback from load to supply, that is why this kind of braking phenomena is called regenerative braking. That means first quadrant cover the motoring action in a particular direction or forward direction, and the fourth quadrant of the converter 1, that will cover the regenerative braking of the motor. Now in case of inverting operation, that means when the first converter are not in working state, then suppose we are applying the triggering pulse across the converter to alpha 2, that can be equal to pi minus alpha 1, whatever, that will be discussed later. Anyways, suppose converter 2 starts working, then the current starts flowing from this direction to this direction. That means the current, the supply current, that is coming from the converter 2 and it is flowing throughout the load in opposite direction of the original one. That means in the first case, when the converter 1 starts working, then the direction of the current across the load was, that is upward or downward direction, which is defined by this arrow I0. When the converter 2 starts working, then the current should flow from this direction, as the both converters are connected back to back. That is why in this particular case the total thing will be in the reverse direction. That will cover these two quadrant operation. Okay, so that is actually for the third quadrant operation. Then the motor starts moving in the reverse direction, and that is actually the reverse generating action or reverse braking during reverse direction of the motor. So we can conclude that when the converter 1 starts working and the motor is suppose moving in a clockwise direction, then the energy is delivered from the supply to motor or supply to load. That is why in first quadrant operation, voltage and current both are positive. And for the fourth quadrant operation, when the converter 1 starts working, then the energy is delivered from load to supply. That means due to presence of back EMF inside the motor. That is why in fourth quadrant operation, here the current is positive and the voltage is negative. Right? Fine. And this is called forward regenerative braking. Okay. Now think about the converter 2. When the converter 2 starts working and normally current is delivering to the load in opposite direction with respect to the converter 1, then the motor starts moving with the opposite direction of the first one, that is in this direction, or that is suppose anti-clockwise direction. That means in this particular case, across the motor, that is voltage and current both are negative. That is called motoring action. But in case of the second quadrant operation, the similar thing, just like a fourth quadrant operation, in the reverse direction, the motor starts delivering energy from load to supply. That is why this is called reverse regenerative braking, which is defined by in which the current is negative and the voltage is positive. Okay, so this is all about the quadrant operation, and due to application of the load, so we can identify that during four quadrant operation is a very good example for using the single phase dual converter, by which we can control the machine, maybe the movement direction of the movement, that is maybe clockwise or anti-clockwise direction, as well as we can change the braking phenomena in terms of with respect of the forward direction as well as with respect to the reverse direction also. And this is all about for the rectification mode of operation and inverting mode of operation. Now the question is arised when the converter 1 and converter 2 both starts working at any instant and with a proper firing angle, suppose alpha 1 and alpha 2, then obviously converter 1 then the current starts flowing from converter 1 to load in this direction and from converter 2 to this direction. That means if the voltage across the converter 1 VO1 and the voltage appears across the converter 2 VO2, if the magnitude will be same, that means the same amount of current starts flowing in the opposite direction across the load. That is why across load there is no voltage is appeared, but due to the change of current for converter 1 and 2, on depending on the firing angle alpha 1 and alpha 2, the instantaneous voltage difference can be occurred, and due to which then maybe there is no current is exist at the in case of load, but there occur a instantaneous voltage difference. That is why the load current may be zero, but a circulating current starts flowing through in between the two converters, and this circulating current that can be limited by this reactor that is defined by LR. The both part is adjusted in the similar way. Suppose that is LR by 2 for converter 1 and LR by 2 for converter 2. That means in circulating mode of operation, the output voltage of the converter 1 and the output voltage of the converter 2, the magnitude may be same. That is why no current is flowing across the load. Then the circulating current starts flowing due to presence of the instantaneous voltage difference of VO1 and VA2, and that is flowing in between the circuit from two converters, and this current somehow can be high in magnitude, that can be actually limited by the current limiting reactor, that is LR. So this is all about for the 3 mode of operation for the dual converter. Now let me discuss about the waveforms. See, here we consider the axis, that is supply voltage Vs, VO1, that is the output voltage from converter 1, and this is the output voltage of the converter 2, as they are connected back to back. That is why if the output voltage is positive from converter 1, then the output voltage should be negative, that is taken from converter 2. And that is the instantaneous voltage difference, which is defined by VR. This is actually appeared across the reactor, that is defined by VO1 minus VO2. That means VO1 minus VO2, that will give us, that is VO1 plus VO2. Okay, consider the first converter, the each switch will be conducted at the point of alpha 1, and the firing angle of the second converter, that is suppose alpha 2. Actually alpha 1 should be equal to pi minus alpha 2 for circulating mode of operation, as both can generate the same amount of output voltage in opposite direction. Okay, so this is the output voltage of converter 1 for RLE load, and we know if the inductor is there, that is why the question for extinction angle beta. Okay, because the question for charging path and discharging path. So charging path can start from alpha to a particular angle pi, and discharging path that can cover suppose pi to beta or pi to next firing angle given to the next circuit. Okay, or next switch. That is why suppose consider alpha 1 is a firing angle. That is why when the thyristors are fired, then the output voltage that should follow the input voltage, and the nature of the output voltage, this is similar to the nature of the input voltage or supply voltage up to the point of alpha. After that, up to the point of pi. After that, from pi to the particular point, that is alpha plus pi where the next triggering pulse has given up to this point, then the output voltage that is will take this shape, that is this one to this one. Next we are applied the next triggering pulse for the next half cycle, then the cycle will be repeated. So this is the waveform from the converter 1. Now in case of converter 2, so before explain this topic, let we assume as the converter 2 is connected in back to back, that is why the output voltage that should be that should follow this type of input voltage. Okay, for easy to explain, we assume this is the opposite nature of the sine wave as the converter 2 is operating in back to back connection. So now consider the firing angle of the converter 2 is alpha 2. That means what? This is alpha 2. That means when the converter 2 is fired, then it starts working. Then the voltage, the output voltage will take this one. It is true that is coming from the negative cycle, but as it is a operation for the rectifier circuit, and we know in case of the rectifier circuit the voltage and current both will be in the same direction, that is why the converter output that will replaced by this peak. As well as up to this point the converter is not working before beta. Before alpha 2 means 0 to alpha 2, there is actually blocking voltage for the converter 2. That is why the total output voltage that can be replaced for the converter 2, that is this one. Okay, right? After that, it starts conducting again unless we are not applying the next triggering pulse to the next half or next half cycle. That is why that can be reflected from this pattern also. And we can draw the total output voltage from the converter 2 from this dotted line, which can be formed by this dotted line. Okay. So this is actually, we have drawn this waveform that can be converted in terms of minus VO2. Actually, we should focus to shape the waveform minus VO2 apart from VO2. But to plot easily, we consider this is the VO2 and which has taken from this waveform. In case of minus VO2, what happened? We can take the mirror image of this one, so it will give this kind of waveform. Right? Now, the instantaneous voltage difference, that is VO1 plus VO2, that means we are going to add this waveform and this waveform. That means at this point of alpha, 0 to alpha, we can have this peak for VO1 and this peak from VO1. Actually, we are going to present the waveform VO1 plus VO2. That is why we can add this waveform and this waveform. So from these two waveforms, we can draw from 0 to alpha, the peak is this one, and for the peak for the converter 2 is this one. That is why we can draw this peak. Okay. Now see, in case of the next part, that is I am talking about alpha 2, that is pi minus alpha. So at this particular point, what happened? There is a concept. So at this particular point, this is the actual area of this peak, right? And similarly, in case of VO2, this is the area of this peak. That means both are same in magnitude but in opposite direction. That is why no voltage, no instantaneous voltage is produced at this particular duration alpha 2 pi minus alpha. Okay. Next, in this case, see, there is a peak that is defined by this one for converter 1, and for converter 2 there is this peak. That means both are in same direction. That is why we can have this peak also for the duration of pi minus alpha 1 to pi. Okay. Now the question for this one. So again, we can see in this particular case the area of the peak, that is this much, and the same duration the area of the peak which is produced by the second converter, that is this one. So both are again in same in magnitude and opposite direction. That is why no instantaneous voltage will appear across this duration. That is, no voltages appear across pi plus alpha 1 to 2 pi plus alpha 1. Right? Again, we can see from the waveform of the VO1, this is the peak is there, as well as in case of the VO2, this peak is there. That is why both are in same direction. That is why this peak can be exit. Okay, and additionally, in this way, the next cycle can be repeated. Now, the question is, that means the actual instantaneous voltage waveform that is defined by this waveform. That is VR equal to VO plus VO2, in which the one peak has arisen from 0 to alpha 1, but alpha 1 to pi minus alpha 1, there is a no peak. That means in this particular case, there is the voltage as the converter 1 and 2, both are in same magnitude and opposite in direction. Similarly, this peak can be erased as they are same for the both converters. Similarly, they are same for the both converters. Again, the both peaks are cancelled by each other as the area of the peak are same, but they are opposite in nature. So in this way, we can form this one, right? So the average output voltage of the converter 1, that can be presented by VO1, that is equal to 2 Vm by pi cos alpha. Actually, this expression can be explained in case of the full converter in case of RL operation, single phase full wave control converter in case of RL operation. So, as we are connected to single phase full wave converter circuit back to back, that is a fast converter which can produce, this is the amount of voltage, that is VDC equal to this one. Similarly, in case of the average output voltage of the converter 2, that can be replaced by this equation, that is VDC2 equal to 2Vm by pi cos alpha 2, where the alpha 1 is the firing angle for the first converter and alpha 2 is the firing angle for the second converter. So, as they are connected back to back and the output voltage, the magnitude can be same. That is why we can replace the equation, that is for first converter VDC1, that should be equal to minus VDC2. Okay, so from this equation we can change and we can put the equation that has been taken from the previous slide. Then we can have the expression, that is 2 Vm by pi cos alpha 1. Okay, that is 2 Vm by pi cos alpha 1, and similarly 2 Vm by pi cos alpha 2. That is why 2 Vm by pi cos alpha 1 equal to minus 2 Vm by pi cos alpha 2. After simplification, we will have the result, that is cos alpha 2 equal to minus cos alpha 1 and cos alpha 2 equal to cos of pi minus alpha 1. So we can write the expression, that is alpha 2 equal to pi minus alpha 1. So this is the relation between two firing angles for converter 1 and converter 2, that is alpha 2 equal to pi minus alpha 1. That is why this can be again reflected on the diagram, on the waveform. See, this is alpha 1 for converter 2 and this is alpha 2, that is defined by pi minus alpha 1, that is for converter 2. So this one is for converter 1, that is alpha 1, and alpha 2 pi minus alpha 1, that is for converter 2. Okay, so it can be explained from this equation. Okay, now what is the value of the circulating current? That can be limited by the current limiting reactor, that is LR by 2 and LR by 2. Actually, the circulating current can be produced by the presence of the instantaneous voltage difference. That can be taken from this waveform. See, from this point to this point, there is a no instantaneous voltage difference, because only we have got the one peak that is actually defined by the second converter. Okay, but here, that is defined by the first converter. And here we have got the result for the two converters. That means we can define the instantaneous voltage difference from pi minus alpha 1 to onward. Again, it can be repeated from the next cycle onward. That is why we cannot confine this instantaneous voltage difference to a particular limit like pi minus alpha 1 to pi plus alpha 1. Okay, that is not a confined cycle. That is why if both the if the operation can be done for the both converters 1 and converters 2, that is actually not dependent on the particular region. That is why we have taken the total value, that is omega t. That means the instantaneous voltage that can be arised from the point of pi minus alpha 1 to omega t. That is why we can express the instantaneous current equation in this way. See, IR, that is actually the current, instantaneous current, which is, that is actually the circulating current which can easily flow throughout the inductor. That is why it can define by I R, and which is the difference between two which is the difference between two instantaneous voltage. That is why we can express the term 1 by omega LR integration of, that is pi minus alpha 1. Just I had discussed before, it had been started from this point, pi minus alpha 1 to omega t, VR d omega t. That is the instantaneous voltage difference. That is actually nothing but that is VO1 plus VO2. That means VO1 minus of minus VO2. Okay, that can be replaced by this term. That means VR equal to VO1 plus VO2. Okay, so we can rewrite the expression, that is 1 by omega LR, that is integration of pi minus alpha 1 to omega t, VO1 plus VO2 d omega t. Again, after simplification, we can rewrite the expression like 1 by omega LR integration of 2 pi minus alpha 1 to omega t, Vm sine omega t d omega t minus 2 pi minus alpha to omega t, that is minus Vm by sine omega t d omega t. Okay, so we can consider the limit part, and by integrating we have got the result, that is Vm by omega LR minus cos omega t 2 pi minus alpha 1 to omega t plus minus cos omega t 2 pi minus alpha 1 to omega t. So this is the integrating value, and considering the lower limit and the upper limit, we can find the expression, that is 2 Vm by omega LR cos 2 pi minus alpha 1 minus cos 2 omega t. So the complete equation for the circulating current that can be defined by C, that is 2 Vm this one, that is 2 Vm by omega LR into cos alpha 1 minus cos omega t. So the total circulating mode operation or inverting mode operation or rectifier mode operation, that depends on this particular value alpha 1. Now consider alpha 1 equal to 180 degree. Then it is then the first converter starts working. If alpha 1 equal to suppose 0 degree, then the second converter starts working. If alpha 1 can vary from 0 to pi by 2, then the first converter can provide the positive current. If the alpha 1 is varies, suppose 180 degree to next cycle, then the second converter can provide the negative current. So in this way we can adjust the alpha 1 by which we can control the converter output in case of the converter output across the load, means across the motor. Then we can easily control the direction of the motor as well as the speed of the motor both. So this is all about for the single phase dual converter with a good example of DC motor. So thank you.